So these are notes for 1.5. There's a good amount here, 4 pages, but we'll see that as we go through the application of this, the homework problems go much quicker despite the quantity on your homework. If we look up at the goal here, we have determining functions, domain range, finding zeros, determining increasing, decreasing constant, even and odd or neither functions, relative min-max, average rate of change. One thing we are not doing is, I'm crossing that out, height of objects under a curve. So that being said, let's go ahead and get into what we have. Just a quick recap, very important. The definition of domain in words is inputs. I'm just going to put I's that have or produce, that produce. I'm just going to produce outputs. And then range are simply our outputs. That's going to be super important as we go through these problems in graphically to determine domain. So what we start out with is if we're determining domain for this first graph here, what we do is we want to look at every x value and see which ones produce an output. Again, it doesn't matter what the output is, just that it produces one. So imagine this red cursor going up and down is a vertical line. If we start down at negative infinity, these are inputs, like here is the x value of 5 at all of these vertical every point on this vertical line, the x value is 5. Well, that doesn't, none of these values produce outputs until we get to this x value, which is negative 1, and that x value produces an output. Again, it doesn't matter what the output is, just that it produces it. So negative 1 is a part of our domain. There are no breaks in the graph until we get up to 4, and that's an open circle. So our domain is going to be from the x value of negative 1 to the x value of 4, but we have open parentheses for the 4 because it does not include it. Now the range is simply the outputs, and we do the same thing, but instead of vertical line, we do horizontal, because our horizontal line is the same y value. So for instance, this is a y value of negative 6, a y value of negative 5, and so on. So we start down at negative infinity, we keep drawing vertical lines until we get to negative 5, and that's our first output. And then we continue up. There's no breaks in the graph right here. There is no output right there, but there is an output right there. So we don't have any breaks in the output so far, and we continue going up. Now look here at 1, at 2, at 3, we have multiple outputs, but that's okay. Remember, different inputs can give us the same output. And we're not listing how many there are of the outputs, just what they are. So we're going from negative 5, and there's no break until we go up to 4. So our range is going to be including negative 5 and including 4 because we don't have open circles at those values. Doing the same over here, if we start out vertical line, our first vertical line that will produce an output is negative 4. There are no breaks in the graph until we get up to positive 4. So our domain is going to include negative 4 and positive 4, and so it's brackets on both. Range, we're going to do a horizontal line. Moving up, first y value is 0 here, and up until we get to the y value of 3, there's no breaks there, and there's no holes at the 0 or the 3, so those will be brackets. Now, if we're just determining from example 1 up here, so this is saying find f of 1, f of negative 1, and also c, which we'll get to in a second for this graph. So what we do is they give us the input. This is a fancy notational way of saying if our input is 1, what's our output? So we go to the x value of 1, which is right here, and we see where does it cross? It crosses the graph right there, and our y value there is 3. So the input of 1 produces an output of 3. Then we go, next one we're doing is f of negative 1, so we look at this, and that produces an output right there, and the output is negative 5. So I just kind of run out of room there, equals negative 5. Here, find the value or values of x such that f of x equals 3. Remember, x is our input, f of x is our output. So they're saying what is our input or inputs with a y value of 3. So now we're not going to do a vertical line of 3. We're going to do a horizontal line of 3. So we go to the y value of 3 and we say what are the inputs that give us the output of 3. We go to here. Our input is 1, and then our other input is 3. So we have two inputs that produce the output of 3, and that is the inputs of 1 and 3. For example 2, we're going to do the same thing. So f of 1 We go to the x value of 1 and we look where it crosses. It looks like it's crossing at about 2.8. 2.9, that should have been an approximate as well, as we see for the second one. F of negative 2, F of negative 2, probably a little more down between, let's see, 3 and 4. Oh, whoops, that's in the first one, it's supposed to be 3.9, not 2.9. And again, for this one, negative 2 goes right there. It's about, go about halfway between 2 and 3, so let's just go with, or 3 and 4, excuse me, so let's go with 3.5. Test where there's these functions, or these graphs are functions or not. Note, disregard here that it's red, blue, and red. It's all the same function, and there's no open circle there. But an input should only produce one output. So if we draw a vertical line of x equals 0 here, we see that input produces two outputs. So since this vertical line crosses in more than one spot somewhere on the graph here many, many times, the answer to this would be no. See if I can write no. There we go. Okay, so here we see if we draw vertical lines that it's only going to intercept the graph once. These are implied arrows. Even though this is looking like it's going close to vertical, it is not. It's cubic, if you recognize it's a polynomial. And so we see moving all the way across, we don't have anywhere that it is intercepting the graph in more than one spot. So the answer is yes, it is a function. Same over here. Let's look at this one. All these inputs produce only one output. If we get to here, these inputs produce 0 outputs. That's okay. That doesn't violate the rule of function. It just means, like, for instance, in our time versus temperature example, we didn't collect any data there. That doesn't violate the rule of it being a function. So this passes a vertical line test, so the answer there is also yes. So vertical line test, we'll go ahead and type this in. Vertical line test, if a vertical line intercepts the graph in more than one place anywhere on the graph, then it is not a function. So it has to be more than once, anywhere on the graph. Next, determine the zeros of a function. 0, the definition of a 0 for a function is an x-intercept because the output is 0. That's where it comes from. So we are going to take, I'm just going to zoom in here, if we take g of x, that's our output. We're going to set that equal to 0. And a beautiful 0. There we go. 0 equals x over 9x squared minus 4. Now we just solve for x. We multiply by the denominator on both sides. This goes over here. I'm not going to write it. That times 0 is a 0. These cancel over here. So we have x equals 0. So our 0, the function, is x equals 0 or 0, comma 0. Next, increasing, decreasing constant of a function. We are going to look at this. If you could please go ahead and read through, pause the video, read through that, and then we will develop the graph together. Okay, now that we are going to the underwater basket weaving with our friends, I hope you got a good giggle out of that. And sorry, I use giggle, part of being a dad of young kids. Okay, so what we're doing is measuring, as time goes on, our distance from our original position, O. So at time 0, you're at your origin. So that would be the coordinate 0, 0. And note, let me say, I'm going to put this in blue just so we can see it. Note, this is also we're going to use the physical understanding, like what physically is happening in this problem relative to the graph to help us understand how to do increasing, decreasing, and constant. Or a review on it as you have seen it before. If it takes you 2 hours to travel a contest and it's 50 miles away, that means at 2 hours, 50 miles, and let's just assume an average rate of change. So we have a line, obviously it's not realistic, but for our purposes here that will work. Then it says that you stay there for an hour, so at 3 hours from our initial time, we have stayed there the whole time, so our distance would remain constant. And then it takes us an hour to get back to our original position, so at a time of 4, we would be at a distance of 0. And now what we're going to do is answer the questions. For what time intervals is your distance from O increasing? That is the same question as where is the function increasing, if any. So the question, for what time intervals, what x values are the y values increasing? So from here to here, our distance from home is obvious, our position O is obviously increasing. So this is an interval from the time of x of 0 to the time of 2, our y values are increasing. Note we always use parentheses in increasing, decreasing, and constant, because we don't have the evaluative skills to determine at the exact time of 0 or at the exact time of 2 what were we doing, increasing, decreasing, or constant. That's what calculus is for, and we're getting to that later as you move forward in math, is if you so choose. Now, when is it decreasing? When is our distance from home or 0 decreasing? From the time of 3 to 4, it was decreasing. That's when we were getting closer to our original position. And then distance from home the same or constant, and that would be from the time of 2 to 3, because from the time to 2 to 3, the graph or outputs are constant. Now, there may be some graphs where you don't have one of those, and then you just put like NA for not applicable, or you could put the null set. Note the null set looks like that. So developing average rate of change, what we're going to do is look at this function. Let's call this point right here x comma 1. And instead of having y sub 1, we're going to call it f of sub 1 of x. We're going to call the output an f of x. And then this point up here is going to be x2 comma f of 2x. This is the exact same thing as x2, y2, and x1, y1, but we're using function notation. Now if we want to find the average rate of change between those, it's going to be the same as we do for slope. It's going to be m equals f sub 2 of x minus f sub 1 of x all over x sub 2 minus x sub 1. Why are we using the function notation? Well, we're working with functions. So we're going to find the output of the function at both values, subtract them, and then divide it by the inputs. So let's say if we want to find the average rate of change of this function x cubed minus 3x, and we want to do it at the first, we want to do it at the x value of negative 2 and the x value of 0, these two right here. If you look at that graph, looks like a positive slope. So let's see what we get. So for a over here, I'm going to write it like this. M sub x equals 0, comma 2. It's going to be kind of the sub value. You don't have to do that, but that's saying what is the average rate of change from, oops, I did that wrong. It should be from negative 2 to 0. So from negative 2 to 0, you don't have to do it that way. So first off, we want to find what the x value or the y value is at x equals negative 2. One way you could do it is look at the graph. Negative 2 outputs negative 2. You could also substitute it in for here, negative 2, and you're going to get negative 2. So negative 2 goes right there. Then at an x value of 0, look at the graph. What is the output? Output 0. That would be the same as taking 0 and plugging it in for here, and we'll get out 0. So we have, so far in the numerator, negative 2 minus 0. And then our x sub 2 is negative 2 again, minus the x value of 0, which is 0. And we look, that would be negative 2 over negative 2, which is a average rate of change of 1. Sorry, it's not a pretty 1 there. So what this is saying is, if the average rate of change from here to here of, let's say, an object's going super fast in one direction, then has to turn around and is going relatively super fast in the other, it did have an average rate of change of 1. And now let's look at the last one, was the average rate of change from 0 to 1. If we look at that, just based on the slope, it looks like a negative slope. Let's go ahead and do the calculations. Do the calculations right here. So this would be m of x equals 0, comma 1 equals, we take the output at the x value of 0. And again, you just plug in 0 into the function, or you look at the graph if it gives it to you. In this case, it gives it to you, so it's 0 minus the y value, sorry. So the y value here is 0. The y value here is negative 2, so minus negative 2 divided by the change in the x's, which is 0 minus 1. And so I have mx equals 0 to 1. It's supposed to be an equal sign, sorry about that. In the numerator we have 2, and the denominator we have 1, and that's an average rate of change of negative 2, which we look over here, that seems reasonable based on this graph.